Welcome! Today we're going to decode a secret language that is literally all around us. You can find it in nature, in music, in math, and yeah, even in the clothes you're wearing. We're talking about patterns, the fundamental rules that build our entire universe.
So let me ask you something. What in the world connects a bee's honeycomb, the chorus of that song you can't get out of your head, and the design on a cool shirt? I mean, they seem totally different, right? But they all share a single, incredibly powerful idea.
The answer? It's patterns. Think about it. Each one, the shape of the honeycomb, that catchy musical hook, the print on the shirt, is built from a simple element that just repeats over and over again, creating something structured and beautiful out of pure simplicity.
Okay, so here's our game plan. We're going to start with the absolute basics, what a pattern even is. Then we'll jump into how they show up in numbers and uncover their hidden rules. From there, we'll explore the incredible symmetry we see in shapes. And finally, we'll look at how patterns can cover an entire surface with no gaps at all. Let's do this.
So, Section 1. What exactly are we talking about when we say the word pattern? Well, it's probably way simpler than you think. It really just boils down to one super simple rule. Again and again.
At its heart, a pattern is just something that repeats. That's it. And that little piece that repeats, whether it's a couple of colors, a few musical notes, or some shapes, that piece has a special name. It's called the core. You can think of the core as the DNA that builds the entire thing.
Okay, let's try a fun one to make this crystal clear. Let's say our core is popcorn, unicorn, mustache. That's our ABC. To build the pattern, we just repeat that core. So you get popcorn, unicorn, mustache. Then popcorn, unicorn, mustache, and on and on. That three-part core is what creates the whole predictable chain.
Okay, so let's take that idea and move from pictures to numbers. The exact same concept of a repeating core still applies, but now obviously we're dealing with digits instead of mustaches. And this is where things start to get really interesting.
Now, when we're talking about patterns in math, we're almost always talking about sequences. And here's the key difference you gotta know. In a sequence, the order is everything. The sequence 1, 2, 3 is completely different from the sequence 3, 2, 1. That predictable order is what makes it a pattern.
And sequences can come in two flavors. They can be finite, which just means they stop, they have a clear end point, or they can be infinite, meaning they just go on forever. And we have a little shorthand for that. Those three dots you always see at the end, that just means, and this pattern keeps going, just like this, forever.
Okay, moving on to Section 3. See, a lot of the coolest number patterns aren't just a simple repeat like 1, 2, 3, 1, 2, 3. No. Instead, they follow a hidden rule, some kind of logic that tells you what the next number in the line is going to be.
And the wild thing is, you've been using these rules your whole life and probably never even thought about it. I mean, just counting. 1, 2, 3, 4. That's a sequence following the simple rule, add 1. Skip counting by t's. 2, 4, 6, 8 is just a sequence following the rule, add 2. You're already an expert at this.
This breaks down the two main types of these rule-based sequences beautifully. On one hand, you have an arithmetic sequence. This is where you just add or subtract the same amount every single time. The analogy here is perfect. It's like walking up a normal flight of stairs, where every step is the same height, steady, predictable. Then you have a geometric sequence. This is where you multiply or divide by the same number each time. And this is like a flight of stairs where each step gets bigger and bigger. It gets tough to climb fast.
So here's what that steady arithmetic growth actually looks like. If we start at 1, and our rule is add 2, we get a perfectly predictable linear increase. We go 1, then 3, then 5, then 7. You could plot this out and it would just be a straight line going up.
But now, look what happens with a geometric sequence. If we start at 1, but our rule is multiply by 2, the growth just explodes. We go from 1 to 2. Okay, but then to 4, then 8, 16, 32, 64, the numbers get massive incredibly quickly. That is the awesome power of multiplicative growth.
All right, time for Section 4. We're going to shift gears now away from numbers and into the visual world of shapes. Here, patterns often show up as symmetry, and that's what creates the balance and beauty we see everywhere, in art, buildings, and especially in nature.
So symmetry usually shows up in two main flavors. First, you've got line symmetry. This is probably what you think of first. You can fold something along a line and the two halves are perfect mirror images, like a butterfly's wings.
Then you've got rotational symmetry. This just means you can spin an object like a pinwheel or a starfish, and it'll look exactly the same at different points during its turn.
And this is where it gets really cool. There's this super elegant pattern when it comes to regular polygons. Those are just shapes with equal sides and angles. An equilateral triangle has 3 sides, and it has 3 lines of symmetry. A square has 4 sides and 4 lines of symmetry. A pentagon has 5 and 5. The rule is just beautifully simple. The number of sides is the number of lines of symmetry, every time.
And this isn't just some abstract math concept, right? Look at a snowflake. It might be incredibly intricate and unique, but its fundamental structure is a hexagon. And just like a simple hexagon, it has 6 lines of symmetry. This hexagonal pattern is all over nature, and for a very good reason. It's the most efficient way to pack things together. It's exactly why bees built hexagonal honeycombs. It lets them use the least amount of wax to hold the most amount of honey. It's a perfect case of a mathematical pattern, creating both beauty and efficiency.
And that idea of efficiency, of fitting things together perfectly, brings us to our final section. What happens when we use patterns of shapes to cover a flat surface completely, with 0 gaps and 0 overlaps? Well, this is the world of tiling, or as mathematicians call it, tessellation.
Just think about the tiles on your bathroom floor or a brick wall. That's a tessellation. It's a pattern made of one or more shapes that fit together like perfect puzzle pieces, covering a whole surface without leaving any empty space behind.
So, what's the secret? How do you know if a shape will tile perfectly? Well, it all comes down to a magic number, 360. At any point where the corners of your tiles meet, all of those angles have to add up to exactly 360 degrees, making a perfect, complete circle. If it's less than 360, you'll have a gap. If it's more, they'll start to overlap.
Now, triangles and squares, they tessellate, no problem. But pentagons, pentagons are a whole different beast. The hunt for these tiling pentagons has this amazing history. After the first few types were found, the list was declared complete back in 1968. But then, people kept finding more. And get this, 4 of the new types were discovered in the 1970s, not by some famous professor, but by Marjorie Rice, a stay-at-home mom with a high school math education who just got curious and started exploring the problem on her kitchen table. It's just an incredible story that shows brilliant discoveries can come from anyone.
So there you have it. That's our journey. We went from the simple idea of again and again in a song, all the way to the complex geometry of tiling a floor with 15 different kinds of pentagons. It just goes to show you how powerful that one simple idea of a pattern truly is.
And that leaves us with one last big question. We currently know of 15 types of these special pentagons that can tile a floor. But after people have been wrong so many times before, can we really be sure the list is complete this time? You have to wonder, what other hidden pattern is still out there just waiting for the next curious mind to find it?